Okay, so first try to understand the autoencoder architecture. So for that we have to see some diagram. So for that we are opening this the autoencoder diagram. So for example, this is the big hierarchy, big overview of the autoencoder part. So basically this is the encoder part and this is the decoder part. So basically encoder is that encoder gets the input of image. For example, here we will give it the our grayscale image with maybe 32 into one size. Okay, so this grayscale image it but encoder does is basically takes this high dimension image into a low dimension latent space. Okay, so latent space is basically some kind of encoding of that image or maybe anything. Okay, so encoder is just try to find the encoding of anything in image. Okay, so this is the encoder. So it try to encode this image into a specific dimension vector. Okay, so then this vector or array, then it the decoder part is trying to reconstruct from this encoded part. Okay, so this is the blended dimension. Okay, so this is the decoder part. So decoder, what decoder does, decoder basically try to map this back into a high dimension image. So basically this is the autoencoder part. So what is that is basically try to first we try to downgrade the image and then upscale the image. Okay, so this is the autoencoder part. What this architecture does, this basically we try to learn the inside, basically the main features of the image which we can use to regenerate some other kind of processes. Okay, so this is very good architecture of the neural network. Okay, so we will try to model this in this our setup to colorize colorize a grayscale image. So here we will provide a grayscale image, or here then we will get a colored image using this network. So this network will try to understand how to colorize a image which is a grayscale. Okay, so moving towards the code. Okay, so here we define the parameters for encoder first and then decoder later. Okay, so this is the input shape. Input shape is the shape of the image. So this is the grayscale image. So image row will be 32, image column will be 32, and one will be the channel size. Okay, channel, because the gray channel only have one channel. Okay, grayscale image. So batch size is the size to train the model. For example, in model in deep learning we try to learn the parameters using in batches of images. For example, we will the model will get the first 16 images and try to make some gradients from it, and then try to learn it the weights of the parameters of the model. But and then again get the next 16, then again 16. So this will map to all the training images. For example, the 50,000 images we got over the above. Okay, so this is the kernel size. Kernel size is basically the size of the convolutional neural network. So basically in CNN we have some convolution filters. Basically we apply to on images to get some basically features of the image. So for that we this is the 3 cross 3 kernel size of the convolutional filter. Okay, so this is the latent dimension. The latent dimension is basically the the encoded dimension of the encoder. For example, this is the latent space. So this is the minimum space, the dimension space which we get up from encoder, and then from this encoded space the decoder makes the resultant image. So this is the latent space. So far we are defining this latent space over here, this which is 256. Okay, so this is the encoder part. The encoder part is the layer filter. For example, the model architecture is something like that. In encoder, what we try to do, we try to basically reduce the image size, but we try to increase the filters. Okay, so for example, if this is if I try to show this is the encoder architecture. What is the shape over here? It is the 32 into 1. Then after one level after, it is the 16 16 64. So you see that the channel size is increasing. but the size of the image is reducing from 16 into 68 into 4 4 into 4, then 4096, and then 256. So this is the latent space dimension. Okay, so this is the encoder part. Okay, so this is the encoder part. So let's say we are trying to this is the encoder architecture. Okay, so we have modeled this. Okay, so uh, we are defining over here. So this is the three layer we are defining for the hidden layer for the encoder part. So this is the convolution 2D layer. So this convolution 2D layer is basically the convolution making the CNN part over here. Okay, so this is the filter and this is the kernel size, this is the stride, and this is the ReLU. ReLU is the activation function for this conv 2D layer. So this is the main conv 2D layer which perform the convolution filters of the over the input image. Okay, so and try to learn the features, and this is some input shape. Okay, so basically here we have defined the input shape, and this is the name of the just model encoder input. Okay, so then we are flattening the image, and then we are defining the decoder part over here. So encoder summary is generating over here. So if I try to run this, so this is the decoder part over here. We also define the decoder part, but for example this from here we are defining the decoder model. So what it does is basically get the same latent dimension as the input. Okay, which we got from the encoder part, but after getting this latent dimension, it is reshaping it, basically upgrading it. For upgradation we are using conv 2D transpose layer. It is the inverse layer like the con 2D layer. Con 2D layer just downgrade the image, and this is upscale the image. Okay, so the kernel size is the same. This is the stride activation function. Activation function is basically try to model the non-linearities in the function. Okay, so this is some upgrade. So we are defining the same decoder function like decoder architecture like encoder. So encoder decoder architecture is similar, just is difference is that encoder is downscaling and the decoder is upscaling. Okay, so this is, so we have tried to run this, and then in this code we just try to show the summary of the decoder, and then we are making the auto encoder, the basically the big model the bigger model which is getting the encoder as well as decoder part. So if you see that this is the decoder architecture, it is getting the 256 input, then converting to 4 into 4 256, then to 888 into 256. So you see when we go downward, the filter size is reducing from 1628 to 64 into 3, but this image size is increasing. So at the end what we got a 32 into 32 into 3 channel. So basically 3 channel is the RGB image, so we got an RGB image. So this is the decoder part, and then this is the auto encoder part. Auto encoder part is basically getting the encoder, decoder, and then decoder. So the complete encoder and decoder is also known as auto encoder. Okay, so this is the total number of parameters for the model, complete model, and then what we are trying to do, we are just after that here we have defined the auto encoder model. Then after that we will define some save directories to save the folder, and then the model name is this. For example, this is the .h file. So this is the file which will have the model parameters stored in it. Okay, so this is the model name, model size, which will have the parameters. Okay, after that we are just checking that if that directory is not available, try to create it, then the file path, and then this is the basically a factor which is the learning rate reducer. So for example, if sometimes during training some due to some higher learning rate, the model is not trying to converge, it is like diverging. So this will try to reduce the learning rate, and this is the some functions or try to reduce the learning rate. So this is the checkpoint. So checkpoint is the like different model parameters values at different states during training. Okay, so for example, when we have